In any case, applications 1.9 of variation. So we'll look at direct variation, which is actually just a proportion. And then I think they call it joint variation, which if you use that in your life, it would be very surprising. I would actually like to know how that would be used. But in any case, also inverse variation, which is, well, the inverse of a proportion. That may not make sense now, but hopefully it will by the end of the day. So, there we go. So when quantities vary directly, they are proportional. Okay, so just like that example we saw from the homework, you just want to make sure if you get labels from these, which you won't always, but if you do, just make sure you stay consistent with where you put the labels, right? Like pounds in the numerator, you'd want to keep pounds in the numerator no matter what fraction you're comparing it with. And then you'd want, bottles perhaps in the denominator, you just keep that consistent, okay? So, the nice thing about proportionality is that they are fractions that are equal, they're just written in a different way, right? And we've seen that, I would say extensively, but maybe not everyone would agree with that. Like 1/2, what's the difference between 1/2 and 2/4? Nothing, just the way that they look. That's the only thing that changes, right? Of course, now they're going to say, hey, this value right here is missing, solve for it. And we found two ways to solve for those last time. Cross multiplication or fish method, and you get to choose which way you like best. Now in direct variation equations though, in direct variation problems, they recommend that you use the equation, and I feel compelled to use the equation because they're going to ask you to write the equation on the homework, all right? Now K is called the constant of variation. This is also known as y equals mx, and for those of you that are familiar with that, it's just missing the plus b part of it. It's just K now is m, the slope. That doesn't have to mean anything right now, but eventually it will, okay? K is the constant of variation, which means that as x changes here, it's changing with relationship to K, right? Like if K is 2, the value 2, you'd take some x value, whatever it is, multiply it by 2, and then you have your new y value, whatever it is, okay? I do feel like I'm talking in circles there. Let me try to clarify what I'm saying here is, right, so some of you perhaps have a job and you get paid, let's be optimistic here, and let's say you get paid $200 an hour, right? Some of you guys are laughing at me, that's fine. I hope someday that you do, okay? But in any case, $200 an hour, right? So y in this case, y would be how much you get paid, x is perhaps how many hours you work, right? You get paid $200 per hour, so as the x value changes, the y value changes correspondingly. So in other words, the more hours you work, the higher the y value will be, okay? And that's why it's called a constant of variation. I guess you'd look at it like speed, right? Like if you drive at a constant speed, not that anyone does, especially in Utah, but, I'm from Utah, so I feel like I'm justified in saying that. So, so if say you drive 70 miles per hour on the freeway, then you drive constantly at 70 miles per hour, then you just multiply that by the number of hours you drive, and you'll figure out how many miles you have driven. That's a direct variation equation right there. All right, find the the variation constant, the K right there, which we just saw, right? Y equals Kx, and I know they're using different letters here, but I just want to point this out, what we saw on the last slide there, y equals Kx. Describe in each situation, if needed, round to 2 decimal places. No problem, we can do that. And it does state on this one that V it varies directly as J. Look, I don't make up the grammar here, okay, but somehow this works and it's proper. For those of you that hate it, it doesn't make sense to me either. All I'm looking for here is, it says it varies directly, so it is a direct variation, which is why we are using y equals Kx right here. Of course, we're using different letters, okay? So here, it says that a study shows that J equals 8 when V equals 2. So we got to solve for K on this one. And what do we see here is that if we kind of have to manipulate this equation, which so on this one, it says that V varies directly. Now, the way that I'm used to seeing this is it would usually say that Y, and yeah, that doesn't matter if that's varies directly directly as x. Okay, so, and again, I don't know why that grammar works, but I guess it does. Okay, so see how the v is the y in this case and the j is the x? Means that this new equation would be written as v equals kj. I'll make the k a different color because it is a constant, right? Now that we have this written, right? So it even gave us these two values of j and v, right? So j is 8, and then the v is 2. So 2 equals, well, still k. We don't know what k is. I mean, some of you do right off the bat there, but not everyone does right off the bat, okay? So we're going to divide both sides by 8 here, and this will tell us the value of k. So for me, I'd say, hey, that's a phantom 1 right there. It's just k equals 2 divided by 8. I would simplify that into 1/4. It did say to, make this 2 decimal places. So 1 divided by 4, that'd be 0.25. So k right here for me shows as 0.25. If we come back to this one, right? So see how the v value, it's 1/4 of the 8 right there. 8 times 1/4 is the 2 right there, right? So that gives us a true statement. And so if you were to change the j value on this one, the v value, no matter what the j value is, it's always 1/4 of that j value because the constant of variation right there. This one is actually telling us y varies directly as x. Well, if x is 2 and y is 3, find y when x equals 1. Yeah, so y equals kx on this one. And yeah, I'll try to use some good colors on this one. Y equals, again, I'll say k is purple. It's just the color I have right here. So y equals kx. And that's, well, y varies directly as x. And then they tell us x is 2. So I replace x here with 2 because this is a correlation that's given to us. X is 2. So I replace x with 2. And then the y value is 3, right? Now this is not going to solve the problem for us. This is only going to give us the constant of variation. After that, after we find the constant of variation, then we can solve for this missing y value when x is 1. And so, yeah, on this one, I divide both sides by 2 to make the, isolate the k, give it a phantom 1 coefficient, however you want to say that. Yeah, we get 3 halves right there, okay? So k equals 3 halves. But again, that does not solve the problem. So we go back to the equation, y equals kx. I'll write this all out, y equals kx, and now we just know the k values. That's kind of a poor k, but I hope it works. So now we know the k is 3 halves. All right, you can put that in parentheses if that helps you to operate there. But now in this new part, it says find the y when x is 1. So I go and I replace the x with 1. This is a direct calculation. In fact, just multiplying by 1 makes that really easy. Anything times 1 is itself. So if x is 1, then the y value would be 3 halves right there. And, well, that's our solution right there. The weekly pay that Melissa receives varies directly, so there we go, y equals kx business, with the number of hours she works. And this, I don't know, I think, or I would hope that everyone has enough experience with this that it would kind of make sense how this is going to be structured, right? If she works 21 hours, she makes $259.56. How much money would she make if she works 35 hours? Now for me, I prefer to write this as a proportion. Do you have to? No. So there's really, I'm going to show both ways that students usually solve this. And I'm not saying they're the only 2 ways even, but you could solve it however you want, okay? So the first thing that students would do is they would find the hourly rate that that Melissa gets paid on this one, which is our constant of variation on this one. So here's the information that it gave us. She's going to get paid $259.56 for, so that's divided by 21 hours. And you can kind of maybe tell that's how that proportion would set up. Now, it wouldn't matter if you put hours in the numerator or the dollars in the denominator. I want to know how many dollars she makes every hour because it's asking then how much money would she make if she works 35 hours. Then it's just a multiplication thing, just like you would with the constant of variation, right? So how many dollars for 1 hour is this? Again, this is the constant of variation. I'm going to go to my calculator because I can't do that in my head. And if you can, that's pretty freaking awesome. But 259.56 divided by 21. Enter, and I get $12.36 per hour, right? So now we're going to take that $12.36 per hour, and you could use dimensional analysis on this one, not that I think anyone would, and just multiply it. See, it's for 35 hours, just multiply it by 35 hours. So let's go back to the calculator, multiply by 35, enter. So you would make $432.60. Okay? So that should be our answer right there. But like I said, there's another method that students usually use on this one, and it didn't specify that we had to use a specific method. So I'm just going to set up a straight proportion, and I'm going to skip that phase of solving for her hourly wages right there, okay? So the first fraction I will set up the same. So it's still $259.56 for 21 hours. But then that second part is for 35 hours, right? So that I see hours in the denominator, so I put 35 hours in the denominator, and then I would solve for x, okay? Now I'm not going to solve that because we already did, right? We already got the answer right there. But whether you use cross multiplication or fish method at that point, you should get the same answer. Now, joint variation, okay? So indirect variation means that one value will go up while the other two corresponding values go up jointly. It says indirect variation. I should say joint variation. Yeah, there we go. Joint variation. So, but we're looking at one value, specifically the y value. It will go up as the x and z values, they should go up, okay? Now, they may differ. We see that the x and z, they're not actually related, or they don't have to be related. But as they change, the y value should go up because we are using multiplication, okay? And then k here is still the constant of variation. Now, we'll look at another method in 1.10 for manipulating this equation to be what you want it to be, which is, I think it's a very useful skill if you can nail that, all right? But for now, we're going to stick with this, and then we'll manipulate it just with principles of equality as we find the values.
Can you go back?
So joint variation right here. And it says, y varies jointly with x and z. So it's going to take on that same format, just like we saw in that last slide. Y equals k x z. Why are they using x, y, and z? I don't know. They're very common letters to use in these types of equations, though. So here we go. Find the constant of variation k if y equals 478.8 when z equals 3 and x equals 38. All right, we can do that. So this one we are solving for the k value, which will then help us to solve those other, the other two parts of this problem. So it did tell us the y value is 478.8. We don't know the k value, so it just stays k. The x value, it says, is, I almost said 3, but 38. And then the z value is 3. So we get this equation, which will help us to solve for k. So yeah, and some people would do that. So 38 times 3, let's just put that in the calculator. Yeah, 114 right there. So now it is 478.8 equals k times 114. And then divide both sides there, just like we would in a regular equation with principles of equality, by 114. This gives us k. So in the calculator, 478.8 divided by 114, enter, I get 4.2. So there's the decimal on that one, and that's okay. But that is the k value right there. Second part, all we're doing is writing the equation, but again, it's not giving us any y value, x, or z value, but it gives us the equation where now we know the constant of, I guess, joint variation here, k, right? So that'd be y equals, we know the k value is 4.2, and then xz. So that's the equation. And so in this next part, where it gives us a z and an x value, it says, hey, find the y value. Okay, well, we can do that too. Let's go and take the equation. So I'll rewrite it here at the bottom. And now it tells us right here the x is 31, so I replace the x with 31. And this skill of just replacing letters with numbers is actually pretty crucial. We're going to see this quite a lot, I think, in the next section here. And then the z value is 22 right there. So I replace the z value with 22, okay? And this is a direct calculation. We don't have to use any principles of equality to solve this. I can just put this directly into the calculator. So 4.2 times 31 times 22, enter, big number, but it works, 2,864.4. That's the Y value. Wind resistance, R, measured in units of newtons, I guess, varies jointly. So varies jointly means we're looking at the same equation, Y equals KXZ, with an object's surface area. I think that's supposed to be A, maybe it's A, I don't know, typo. And velocity V, an object traveling at a velocity V equals 14 miles per hour with a surface area of A equals 3 square feet, experiences a wind resistance of 33.5 newtons, which, see how that gave us V, A, and R. And that's all three of those variables, which means that then we can solve for the corresponding K constant of variation on that one. So find the constant of variation. There's what we need to do. And we'll round to 2 decimal places if we need it. Please note the value of the constant of variation K is only valid for the problem given above. Oh, interesting. All right, well, whatever. So, Y equals KX on this one. That is our equation for joint variation, right? But now it's given us new variables. It says R varies jointly, so the R is the Y in this case. There's the R. Equals a K, doesn't matter, it's still K. But then X and Z right there, it's not going to matter. It's either velocity or surface area. I don't know. I guess I'll put this as AV on this one, okay? Would it matter if you put VA? No, it wouldn't. It wouldn't. You'd get the same answer. But now we can put in the values that it gave us. It says right here that R is 33, that's the resistance, 33.5 newtons. And then where's the A value there? I know it's here somewhere. 3 square feet. There it is. Found it. 3 square feet for A. So let's go in there and replace that A with 3. And then the V, 14 miles per hour. So we'll replace the V with 14. So this will allow us to solve for the K value, the constant of joint variation. So, well, let's see, 3 times 14 should be 42. So 33.5.
Whoa.
I know not everyone would need to write all this out, but that's fine. And now divide both sides by 42. 2. Make that coefficient of K1. K, our constant of joint variation, 33.5 divided by 42. Enter. This one's telling us to round this to 2 decimal places. So 0.79761948, that's what I got. Yep, that'd be because the 9 would have to add 1 to the 9 in the hundreds place value. So 9 plus 1 is going to make that carry a 1 over into the tenths place value, so 0.80. Just from that, we do have our constant of joint variation. So now using the constant of variation K from above, write the joint variation equation for wind resistance R in terms of V and A. All right, no problem, we can do that. So R, and that we kind of had it up here, right? So that's R equals K, but we now know K is 0.8. I'll still keep the 0 to be a little bit more specific. And then we had AV, right? Try to keep these kind of color coordinated. But that would be the equation. And then this last part, using the variation equation from above, R equals 0.80 AV. Find the wind resistance of a similar object in similar conditions with a square footage of 32 as the surface area and the velocity 24 miles per hour. No problem. In fact, you know what? I'll do this on the right over here. All right, so there's our equation. And over here it says that the A value, I guess I'll start with A, 32 square feet. So I'm going to go back to my equation and replace the A with 32. Right there. And then the V, 24 miles per hour. So V, replace that with 24. And just put this in the calculator. So yeah, just putting that in the calculator, we get 614.4. I guess, you know what, we'll label this newtons, just put an N right there. So resistance, 614.4 newtons. There we go. All right, this one is an indirect variation. So this is telling us that when one value goes up, the other corresponding value should go down, right? And I mean, there are real life examples of inverse variation, right? Like the longer you drive, so as the distance you drive goes up, the amount of gas in your tank would go down. Or you could do it with the phone, right? If you use your phone for a long period of time, then the amount of battery you have in your phone goes down, assuming it's not plugged in. So this works. K equals xy now on this one. See how the y and k switched? So that's why it's considered an inverse. And so to find the y value, you've got to take the constant of indirect variation and divide it by the x now, which is just a form of manipulating the equation, which again, we're going to see that how this forms in 1.10, okay? But that's the indirect variation. Well, I don't know. I feel like if I add more to that, it would make it more confusing, but we'll keep it there. Yeah, y varies inversely as x, and again, the wording there, I don't make up the wording, someone else does. If x equals 8, then y equals 6. Find y when x equals 2. Now you see how the x value's gone down. That means that the y value, since it's an inverse variation, should have gone up, right? And find the constant of variation, no problem. We'll round the answers to the nearest hundredth if it's needed. So here we go. Going back to the equation here, y equals k over x. Well, you know, I probably should skip that one. Remember the other equation was k equals xy. Yeah, this one will help us out. It'll give us the k value directly. Because here we see that x is 8, so I'm going to replace x value there with 8. I'll put in parentheses, and then the y value here is 6, so replace the y with 6. And this will allow us to solve for the constant of inverse variation, which appears to be 48. So yeah, that is, by the way, that's one of the boxes you'd have to fill in. Now the other equation, y equals k over x, I can use that because now I do know the k value, which is 48. But here, the new x value is 2, right? Find y, because we don't know this y value, when x is 2. So I'm going to replace that x with 2 and just solve for y. No problem. And what do you get? 48 divided by 2 is 24. So I can do a better y than that. Y, when x is 2, y is 24. See how that x, again, hopefully this makes sense, right? The x value was cut in a fourth, right there. It was divided by 4. So correspondingly, in an inverse variation, the y value was multiplied by 4, right? X was divided by 4, y gets multiplied by 4 to get 24. And if you saw that on the surface, you could have done that directly, but you still would probably have to find the constant of inverse variation right there. There's always a problem like this, and it always causes a lot more problems than I wish it did, but it does, okay? So maybe it's the next one actually that I'm thinking of. Whatever the case. The water temperature in the ocean varies inversely with the depth of the water. Yeah, this is not it. I apologize. The deeper a person dives, the colder the water becomes. See how the inverse variation, as you go down, the numbers get bigger, the temperature gets smaller, yeah. At a depth of 1,100 meters, the water temperature is 7 degrees Celsius. I don't know why it's underlined. What is the water temperature at a depth of 900 meters? Okay, so yeah, we do have to find the constant of variation first, no matter what. Okay, so that's what we'll do first. So k equals xy. Now this does not solve the original problem, but it will help us to. K equals xy. So the x value, it doesn't matter which is which. It says the depth is 1,100 meters. And then it tells us temperature is 7 degrees Celsius. We're just going to multiply these two to find the constant of inverse variation now. 7,700. And it has no label, doesn't need one, because it's just a constant. But now that I have that constant of inverse variation, I should say inverse variation, but what is the water temperature at a depth of 900 meters? Okay. So the depth, let's see, I have the depth here in green, so I'm just gonna keep it, I'm gonna keep it there. Let me think how that would work. So, yeah, y equals, remember the y equals, k over x, like this, okay? So, we now know the k value is 7,700. And the x value, doesn't matter which is which. I'm gonna say that that is depth now, which showing is 900 meters. And yeah, the original was in meters. So let's just divide these and just cancel those out. So 77 divided by 9, 7,700 divided by 9, either way. So I get 8.5 repeating. It said, it did not say where to round this to. I'll do 2 decimal places,
No, it's not
8.56. And you may be wondering, well, how can I be for sure that the x is the depth? And because it doesn't matter with an inverse variation, it does not matter. And that comes back to equation manipulation. You can interchange the x and y in this one because, well, it's principles of equality really, but it's equation manipulation, which comes in the next section there. And if you think about this one, I think it makes sense, right? Because is the temperature changing because of the depth? I mean, that's the way that I would look at it. So the temperature for me depends on the depth, which would make the depth x. But could you say that that the depth is changing based on the temperature? I mean, you know, depending on your outlook. I'm not saying it's right, but it would still work in this scenario. All right, here we go. This is the one. This is the one that most students struggle with. Okay, now it's only one problem. I've had students in the past, I'm not recommending this, but I've had students in the past who are like, I hated that so much I just skipped it. All right, you know, you're an adult, okay? But I'm not recommending that you don't because we're gonna go over it. A problem that's similar. The loudness L of a sound measured in decibels is inversely proportional to the square of the distance. Now that's the part that gets us because they're not gonna give you this formula right here. But it's the square of the distance, right? So that means you take the distance and you gotta square it. All right, and that's the important part. Square the distance from the source of the sound. Now, hopefully that makes sense, right? The farther you are away from whatever's making some sound, the less loud it would be. You know, whether it's a jackhammer or a jet plane engine, the farther you are away from it, the less loud it should be. But this one says a person 11 feet from a jet ski, it is 92 decibels loud. How loud is a jet ski when the person is 53 feet away? We will need to find the constant of inverse proportionality on this one, even though I don't think it's going to force you to on this, but you're just going to have to one way or the other. All right, so let's find that K constant right there. And, you know, I'll just bring this over. All right, so on this one, the decibels loud, that's L. Right there, 92 decibels loud, that's our L value right there. So I can go into this formula up here for K and replace the L with 92. I can write that bigger. Sorry about that, 92. And then it says it's 11 feet from the jet ski, right? So there's 11 feet from the jet ski. So let's go and replace D. Now that's D to the power of 2. That's important to remember, though. It's 11 feet from the jet ski. You just got to square it right there. And this will give us the K value. So I'm just going to plug this directly into the calculator. 92 times 11 to the power of 2. If you're looking for the power of 2 button, it's just one button to the left of 7. There are other ways to put in a exponent, but that's what I'm going to use. So I push enter. Oh, it's a big one. 11,132 is our constant of inverse variation for this one. But now that I have it, I can go into this next part. How loud is the jet ski when the person is 53 feet away? All right, that's the distance right there, 53 feet away. So I'm going to replace the 53 feet away with D. Okay, so let's bring that formula back down over here. So, not this one, sorry. Let's use this one because we want to know the loudness now. And yeah, we now know that K is 11,132. So let's go ahead and fix that one up first, okay? So 11,132 32. And we now know that the distance here we're trying to find is 53. So there's a 53 to the power of 2. I'll extend that fraction line so it looks a little bit better. And this will tell us the loudness, right? Because I am curious now.
80
All
on.
right, so let's put this in, if I can. Let's see if I can type it in correctly this time. 11,132, I just double checked. I got that in right. Divided by 53 to the power of 2. Enter. Okay, yeah. Yeah, that's correct. I got 3.9629, and I'm not gonna have to go any further than that because it's rounding 2 decimal places.
Yeah.
Use the 6, circle the 2. That's less than 5, so just keep it the same. 3.96. Yeah, so thank you for pointing that out. Yeah, that's decibels. Remember, it is okay to get things